is a remarkable piece of real estate, and a busy one at that. From ever-changing weather patterns to the hustle and bustle of city streets, our planet is in a constant state of motion. However, if we take a look just below the surface, we find that things are always moving below our feet as well. It's called plate tectonics, and it's how the continents were formed and reformed and reformed.
But before we get to that, let's dive underground to learn what our planet looks like from the inside and out. Our Earth is made up of layers, and there are two types of layers we need to learn about in order to understand plate tectonics. The compositional or chemical layers and mechanical layers. We could spend an entire session on what makes both of these types of layers unique. But before this lesson, we're simply going to provide an overview. There are three primary compositional layers to the Earth's surface, and these are probably the ones you're most familiar with: the crust, the mantle, and the core. It's important to understand that compositional layers refers to the Earth is made of. However, if we take a look at how the inside of the Earth behaves, we can divide them even further into mechanical layers. Starting from the outside, working in the lithosphere is the outermost layer of the Earth, which contains the entire crust in the topmost layer of the mantle. The asthenosphere contains the same materials as the top layers of the mantle, but the pressure in the heat increase. It's not exactly a liquid, but it does move like heated rock, so you could say it's somewhat fluid. The mesosphere is next. At this level, the pressure is really starting to build, which restricts the molecule's ability to move, thus making it very, very rigid. Past the mesosphere is the liquid outer core. Extremely high temperature melt the metals contained in this layer into liquid form. Think flowing rivers of lava and you'll have a pretty good idea of what the outer core is like. And finally, we reach the solid inner core. Just like the liquid outer core, the inner core has extremely high temperatures and is composed of mostly metals, which might lead you to ask, why isn't it liquid as well? The answer is pressure. There is so much pressure at this depth that even though the temperature are beyond the melting points of the metals contained in the inner core, the high pressure essentially squishes everything down into a solid. Now that we know a bit more about the composition of the Earth, let's move on to the plate tectonics. Let's start with the history.
A scientist named Alfred Wegener noticed that the coastlines of several continents look like they fit together, similar to puzzle pieces. He believed that around 200 million years ago, all of the continents were joined together in one large supercontinent that he called Pangaea, which is Greek for all the Earth. Over the course of millions of years, Pangaea broke apart into the continents we know today, a process he called continental drift. Although his theories explained quite a bit about the origins of the Earth, scientists at the time weren't exactly impressed and initially dismissed his ideas. Fast forward to today, and Wegener's concepts are the basis of the modern-day plate tectonics theory. This is the plate tectonics theory. Well, it states that the Earth's outer mechanical layer, the lithosphere, is divided into large continent-sized plates that are constantly moving. How fast are they moving? Pretty slowly, actually, around 1 to 2 inches per year, which is why it was so hard for scientists 100 years ago to wrap their heads around the idea. So what changed their minds? Well, a few natural discoveries in the 20th century made Wegener's theories seem more plausible. For example, in the 1950s and 60s, scientists discovered heated magma rising up through cracks in the oceanic crust called dikes, which is how new rock or new land is created. This realization that our planet is always reforming and reshaping itself from beneath lent credibility to Wegener's theories. Point Wegener. Not long after, scientists started plotting the location of earthquakes and volcanoes around the world and observed that the location of those events followed a similar pattern to the outline of the plates Wegener proposed. And then there was the fossil evidence. Fossils of tropical animal and plant species have been found in Africa and other places on Earth that are less than tropical. One plausible explanation was that Africa was once part of a larger continent that was home to these tropical plants and animals. Remember Pangaea? So in light of all this evidence, the scientific community started thinking, probably onto something, which led to the development of our modern-day plate tectonics theory. It all works. According to the plate tectonics theory, these massive lithospheric plates are all moving in different ways, and how they interact with one another can have a huge impact on the Earth. Where these plates meet are called boundaries, and there are three kinds. Convergent boundaries occur when two plates are moving towards one another. Transform boundaries occur when two plates are sliding past one another, and divergent boundaries occur when two plates are moving away from one another. Let's take a closer look at what happens at each of these boundaries. As we said, convergent boundaries are when plates are moving towards one another. When the two plates collide, a couple of things can happen. One of the plates will dive under the other plate. It's usually the heavier, denser crust that dives under the lighter crust. This creates what is called a subduction zone. And the deeper under the Earth's surface that plate goes, the more pressure it creates. That pressure, coupled with the high heat, causes the crust to melt, forming magma. The magma presses up towards the surface, and voila, you've got a volcano. An example of this is the Ring of Fire, which is an active ring of volcanoes that encircles the Pacific Ocean. The other thing that can happen when two plates press into one another at a convergent boundary is the rock above the boundary will be lifted up or folded and form mountains. Ever hear of the Himalayas? That's an example of two tectonic plates colliding. And because the plates continue to move, the peaks in this mountain range continue to grow. For example, Mount Everest, which currently measures around 29,000 feet, grows around an inch every year. So as you can imagine, it takes thousands of years for these mountains to form. But although movement at convergent boundaries is usually gradual, as pressure underground builds, the impact above ground can be quick and violent. Fast movement or slipping of land can result in earthquakes either above ground or under the ocean. And convergent boundaries aren't the only type of boundary that can result in earthquakes. At transform boundaries, the Earth's plates are sliding past each other in opposite directions, which creates a crack or fault in the Earth's crust. As the plates try to move, they rub against one another, resulting in the building up of pressure. If the plates are stuck for a long period of time, the pressure will continue to build at the fault line until eventually it releases, resulting in an earthquake. The San Andreas Fault System is one of the largest transform boundaries in the world, which is why that area has more than its fair share of seismic activity. That just leaves divergent boundaries. Like we mentioned before, divergent boundaries occur when plates are moving away from one another. Either the space between the two plates widens and becomes a large crack or rift, such as the East African Great Rift Valley that runs from Lebanon to Mozambique, or if the space between the two plates is under the ocean, where the crust is thinner, magma oozes up from the Earth's mantle and fills the space. This is called seafloor spreading. The Mid-Atlantic Ridge is an example of where seafloor spreading has occurred. The crust under the ocean pulled apart, allowing magma to fill the space between, creating the tallest and longest mountain chain in the world. So in review, the plate tectonics theory is based on concepts first proposed by Alfred Wegener in the early 20th century. It states that the Earth's outer mechanical layer, the lithosphere, is divided into large continent-sized plates that are always moving, leading many scientists to believe the continents we know today were once part of a supercontinent called Pangaea. These plates moved 1 to 2 inches per year. Where they meet is called boundaries, and there are 3 different types. Convergent boundaries, where plates collide, transform boundaries, where plates slide past one another, and divergent boundaries, where they move apart. Volcanoes and mountains form at convergent boundaries. Earthquakes and tsunamis can occur at both convergent and transform boundaries. Fissures and large cracks in the surface occur when 2 plates move apart at a divergent boundary. And seafloor spreading occurs at divergent boundaries located at the ocean floor.
Hi guys, good day. My name is Precious C. Broca from grade 11 Cubes Democratus. My topic is about continental drift. This video will show us history or how the continental drift. Scientists have long recognized that Earth became the hot molten mass. But a century ago, it's popular theories that mountain ocean bases in cause of vertical motion of the crust is a planet cold.
It was suggested that contraction of the planet produced features on the surface that were analogous to creases and folds of a baked apple.
At the same time, geologists were examining rocks and fossils to make interpretation of higher Earth physical environments, and change for a planet is great. But this finding growing realization that Earth had changed. Everyone seemed grilled in the fact that the continents and ocean has remained and fixed over time. Alfred Wegener was a German meteorologist who did research on Greenland and studied Asian climates. He collected data from several different sources to generate a new and controversial hypothesis that came to be known as continental drift. Beginners suggest that the world's major land masses had formed a single supercontinent named Pangaea, and that rather than moving vertically, Earth was dominated by horizontal motions as the continents drifted across its surface. Gene makes up something like this. Can you believe if the shape the most continents for her today will form Pangaea become land masses drifted by locations?
Wegener had four main lines of evidence in support of continental drift. These included the fit of the continents, the match of mountain belts and ancient rocks, indications of past climates, and the distributions of fossils.
Start with the fit of the continents. Wegener is the first person noticed the shape of some continents since contributor. The most obvious match for southwest portion of Africa and the northeast pole South America. And there are the sum of discussion.
The fit is even better if we use the outline of the shallow continental shelf rather than the edge of the land. And now we can see that the curved northwestern edge of Africa seems to match the eastern margin of North America.
Notice that India, Australia, and Antarctica are tucked together on the other side of Africa, not too far from the present-day South Pole. And Eurasia, that is, Europe and Asia, is further north than its current location.
Let's look at the second Alfred Wegener's checklist. Match the matching mountains and the rock types.
Continents on either side of the North Atlantic Ocean have mountain ranges of similar age and structures. These include mountains such as the Appalachians in North America, the Atlas Mountains in Africa, and the Highlands in Scotland.
If we take Pangaea from 300 million years ago and superimpose the modern continents, it would look something like this. Notice that the separate mountain ranges now come together to form a single chain of mountains that formed when continents collided to create the northern half of Pangaea.
If we take the same template and now look at distribution of ancient cratons representing rocks 11.2 billion years, we find another match between Africa and South America.
So now we have evidence for Pangaea from two types of data. What about climate reconstructions?
As you can see from the map, many of the southern continents were located at the high latitude, close to the South Pole rocks from 300 million years ago, and the continents show evidence from presence of massive ice sheet even larger than Antarctica today. Striations, scratches in the bedrock floor by glaciers are common in rocks of these regions and indicate the ice sheet was moving towards the interior of many of the continents from a central high point. Somewhere to the south, if the continents had always been in their present location, a truly massive ice sheet would have been Israeli and would have required global-scale Paleocene. However, there is ample evidence that elsewhere in Pangaea were a lot warmer, forming tropical pole swamps along the Pangaea equator in hot deserts further south.
The same locations today would have very different climates, so these patterns only make sense if the continents were part of Pangaea. Finally, what about fossils? How can they be used to support the concept of continental drift?
Let's jump forward about 50 million years and examine what was going on in the southern half of Pangaea. We are going to consider 4 different fossil species found among multiple continents. They represent two land-dwelling reptiles, another that live in coastal environments, and a plant with seeds that were too heavy to be carried great distance by winds. Some modern-day crocodiles, wolves, and pigs didn't swim across the ocean. The only way to find the same organism on different continents was to have a single giant landmass so that all the organisms could move easily between locations. When the continents split apart, the rocks containing the fossils were preserved on different sides of the oceans.
So we've checked all the boxes for Wegener's evidence in support of continental drift. What do you think? It seems pretty convincing, doesn't it? But it turned out it wasn't convincing enough for Wegener's contemporaries.
First of all, trying to get people to dramatically change their views about something is very difficult. Many geologists of Wegener's time refused to accept this paradigm shift in thinking about Earth's continents and came up with other explanations for Wegener's observations.
But most importantly, Wegener didn't have a good explanation for what caused the continents to move. Without a cause for continental motion, his drift hypothesis did not gain wide acceptance.
It would take another 30 years before other scientists made a series of new observations about Earth that led to the development of the theory of plate tectonics, which confirmed several aspects of Wegener's hypothesis. Unfortunately, Wegener died on the Greenland ice cap at 50 years old and didn't live to see his ideas verified.
Hi everyone, I am Lizel R. Questoria. Today we will discuss about the evidences of continental drift theory, and we will have some videos here to show it to you. What is continental drift theory? It is included the fate of the continents and distribution of ancient fossils, rocks, and mountain ranges, and the locations of ancient climatic zones. There are various examples of fossils found in separate continents and in no other regions. Here are some evidences supporting continental drift theory. First, the matching of continents, that is, jigsaw fit. It is the coast of the South America and the west coast of Africa seem to fit together like a piece of a jigsaw puzzle, and Wegener discovered the rocks layers fit just as clearly. South America and Africa were not only continents with similar geology.
If you look at the shorelines of Africa and South America facing each other, and if I bring them together, they are a good match. This fit of the Atlantic margin was presented by Edward Bullard in 1964. So this forms the first evidence in support of the continental drift theory.
Second, rocks of the same age across the oceans. That Wegener said the rocks had formed side by side and the land had since moved apart. Mountain ranges with the same rock types, structures, and ages are now on opposite sides of the Atlantic oceans.
Radiometric dating is a technique used to date materials such as rocks or carbon. So after using this technique, they came to a conclusion that all the rocks from different continents have a correlation. For example, the belt of ancient rocks of 2000 million years from Brazil coast matches with those from Western Africa. Then it also suggests that the marine deposits in the region is from the Jurassic era. Jurassic era is the second phase of Mesozoic era, where the reptiles rule the continents. And this forms the second evidence in support of the continental drift theory.
Third is stelite. These rocks deposits, which date from roughly 286 million years ago, bear a strong similarity to deposits found in other southern continents such as Africa.
Rock formed out of deposits of glaciers. Mostly you'll find them in colder regions. They look something like this. So the Gondwana land, which is the southern part of the initial Pangaea landmass, is known to have broken into 6 different landmasses. They are Africa, Falkland Island, Madagascar, India, Antarctica, and Australia. Now at the base of all these landmasses, stelite have been found, which proves the fact that all these 6 landmasses have similar histories. Since it is not possible to go back in time to see what climates were like, scientists use imprints like these that are created during past climate to come to a conclusion that continents are really drifting away. Oh, by the way, just a quick info, paleoclimatology is the study of past climates. Therefore, stelite forms the third evidence in support of the continental drift theory.
Next, placer deposits. Placer deposits are masses of unconsolidated and semi-consolidated clastic sediment formed by surface weathering and erosions of primary rocks that are subsequently transported by gravity, water, wind, or ice from their original source and redeposited elsewhere.
The deposits is an accumulation of valuable minerals like gold, diamond, etc. If you look at Ghana, the Ghana coast is rich in placer deposits of gold. Usually gold is extracted from rocks, but here in Ghana, gold is found in placer deposits and not in rocks, which is kind of an amazing fact. And if you go to Brazil, the same gold placer deposits are available there as well. Therefore, it is obvious that gold deposits of the Ghana are derived from Brazil Plateau, another evidence that supports the continental drift theory.
And lastly, the distribution of fossils. Fossils are found in Australia, South Africa, South America, India, and Antarctica. When the continents of the southern hemisphere are reassembled into a single landmass of Gondwana land, and the distribution of these four basalt types form linear and continuous pattern of distribution across the continental boundaries.
Landmasses. That provides a strong evidence that everything once upon a time was a single large landmass. Lemur is one such species that is very famous in Madagascar. Now fossils of this species was also found in India. Though it is said that lemurs originated in Africa, linking these three landmasses, you can easily see there is a correlation. Similarly, Mesosaurus is a reptile. It is an extinct species. It is no more available, so skeleton of this reptile has been found in regions of Southern Africa and South America. Again, it is reinforcing the fact that these two continents were once linked together. So these were all the evidence that speaks in favor of the continental drift theory facts, and one must broadly remember them in order to understand the origin of continents and oceans, and how it led to the adaptation of animal and plant species, which today is the main reason behind diversity of life.
That's all for today. Thanks for watching.
The Earth's outer shell, the lithosphere, consisting of the crust and uppermost mantle, is divided into a patchwork of large tectonic plates that move slowly relatively to each other. There are 7 to 8 major plates and many minor plates. The major plates are Pacific Plate, North American Plate, Eurasian Plate, Australian Plate, African Plate, South American Plate, and Antarctic Plate. To make it easier to remember, consider the 7 continents of the Earth, but in this case, Europe and Asia are combined to form the Eurasian Plate. In addition is the Pacific Plate. Varying between 0 to 100 millimeters per year, the movement of plate is driven by convection in underlying hot and viscous mantle. Let's recall that convection currents are identified in Earth's mantle. Heated mantle material is shown rinsing from deep inside the mantle, while cooler mantle materials sinks, creating a convection current. It is thought that this type of responsible for the movement of the plates of the Earth crust. Earthquakes, volcanic activity, mountain building, oceanic trench formation occur along plate boundaries in zones that may be anything from a few kilometers to a few hundred kilometers wide. There are 3 main types of plate boundaries. Are edges where 2 plates meet. This type of plate boundaries are convergent plate boundary, divergent plate boundary, and transform plate boundary. The word convergent is the adjective form of converge, and synonyms of collide. In simple words, converge means to come together or to meet at one point. In convergent boundary, the blades are colliding as shown in the figure. Subduction zones occur when one or both of the tectonic plates are composed of oceanic crust. The denser plate is abducted underneath the less dense plate, the plate being forced under and eventually melted and destroyed. Convergent boundaries occur when tectonic plates move towards each other and strike one another. If you look at this map of the major plates, you can notice have it all that are convergent boundaries. As this plate moves and strike one another, you may get earthquakes, volcanoes, or deep trenches. There are 3 types of convergent boundaries: oceanic and continental lithosphere, oceanic and oceanic lithosphere, and continental lithosphere. Continental convergent boundary occur when oceanic crust subducts underneath the continental crust. The oceanic lithosphere has a greater density than the continental lithosphere, and as it collides with the continental crust, it subducts underneath the continental lithosphere. As it sinks, magma forms and begins to rise to the surface and may form volcanic mountains. Continental lithosphere. When continental strikes continental lithosphere, neither crust subducts nor is magma. Earthquakes occur. Earthquakes may also occur and deep trenches may be formed. An example is when the oceanic Nazca plate subducts underneath the continental South American plate. At this location, the Atacama Trench has been formed in the ocean and the volcanic mountain eschar located to the land. When the oceanic lithosphere collides with oceanic lithosphere, A similar event occurs. The older oceanic crust is denser than the younger crust and subducts underneath. As it subducts, magma begins to rise to the surface, and this can create volcanic island oils. An example is the portion of the North American plate covered with ocean subducts underneath the Pacific oceanic plate. The Aleutian Islands have been created from this collision. When continental strikes continental lithosphere, neither crush or subduct nor is magma. Earthquakes occur.
These two Graham crackers illustrate what happens. The two plates buckle and create folded mountings. An example is the Indian plate colliding with the Eurasian plate and creating the Himalayan mountain range.
So those are the different types of convergent boundaries. The second type of plate boundaries is divergent plate boundaries. The word divergent means to divide. In simpler definition, it means to move away from each other or to separate. Divergent boundaries, where two plates are moving apart, the space created can also fill with new crustal material sourced from molten magma that forms below. Divergent boundaries can form within continents but will eventually open up and become ocean basins. Divergent boundaries occur when the huge tectonic plates move away from one another. This occurs above rising convection currents. The rising magma pushes up on the bottom of the lithosphere and flows laterally beneath it. This lateral flow causes the plates to move in the direction of the flow. At the plate's boundary, the two plates move in opposite direction. Divergent boundaries are constructed boundaries because new crust is formed. As the plates move apart, molten magma fills in the gap and creates new crust. If you look at the map of the major tectonic plates, you can see several divergent plate boundaries. There are two major types of divergent boundaries. These are continental and continental lithosphere, oceanic and oceanic lithosphere.
Oceanic and oceanic divergent boundaries occur when two oceanic plates move away from one another. This is where seafloor spreading takes place. The most common example is the mid-ocean ridge, which stretches around the world. The mid-ocean ridge can be seen here in red. Divergent boundaries are constructive boundaries because the rising magma creates new oceanic crust and lithosphere. The mid-ocean ridge runs right through Iceland. Here's what it looks like on land. Imagine this same formation. Underwater continental and continental divergent boundaries occur when two plates of continental lithosphere move away from one another. As the magma rises, a new lithosphere is created.
The East African Rift Valley was created when continental and continental divergent boundaries move away from each other. The Red Sea is another example. The Red Sea was formed by the divergence between the African plate and the Arabian plate. The rift transmitted eventually from a continental and continental to a continental at an oceanic plate boundary.
Transform boundaries where plates slide past each other. The relative motion of the plates is horizontal. They can occur underwater or on land, and crust is neither destroyed nor created.
Because of friction, the plates cannot simply glide past each other. Rather, stress builds up in both plates, and when it exceeds the thresholds of the rocks, the energy is released, causing earthquakes. Let's move on to folds and faults. These two geologic terms are both of crust deformation. Deformation involves change in shape and or volume of substances in the rock. Faults and faults are also visible effects of plate tectonics or movement of lithospheric plates. Faults are bends in rocks that are due to compressional forces. Compressional force occurs when a physical force presses inward on an object, causing it to become compacted or squeezed. Faults are most visible in rocks that layered, also known as sedimentary rocks. Faults are formed when heat and pressure are applied to the rocks. The higher temperature, the more pliable rocks become. Faults are more likely to occur when the deformation caused by the compression is applied slowly. Faults of alternate layers of limestone and current occur in Greece. The limestone and quartz were originally deposited as flat layers on the floor of a deep sea basin. These faults were created by alpine deformation. If the pressure or compression that is applied to a rock undergoing a fault is greater than the internal strength of the rock, then the rocks will fracture. This is how faults are formed. Faults are fractures in Earth's crust where rocks on either sides of the crack have slid past each other. Faults are defined as the displacement of rocks that were once connected along a fault line. Sometimes the cracks are tiny as thin as hair, with barely noticeable movement between the rock's layers, but faults can also be hundreds of miles long, such as the San Andreas Fault in California and the Anatolian Fault in Turkey. Both of these are visible from space.
Hi guys, my name is Jason Ifera. My topic is all about how the sea floor spread. My first explanation is sea floor spreading occurs at divergent plate boundaries as tectonic plates slowly move away from each other. My second explanation, there are three types of plate-plate interaction based upon relative motion: convergent, where plates collide, divergent, where plates separate, and transfer motion, where plates simply slide past each other. The theory of sea floor spreading states that the new ocean crust is continually being formed, and that this crust is slowly carried away from its point of origin over a period of time. The study of the repeated reversal of the Earth's magnetic poles over time has provided convincing evidence of the seafloor spreading.
Hi, my name is Jemar Philip Embolitik. The structure and evolution of the ocean bases. Explanation 1. The ocean bases constitute one of the two major topographic features of the Earth's surface, the other being continents, yet they also feature such as oceanic ridge, trenches, and fracture zones and cracks, abyssal plains and hills, seamounts, and goyats. Explanation 2. A1. The upper crust is the deformed biductal stretching, with the lower crust is broken along normal faults. 2. The tension pulls apart the crusts and crust slab sink in the middle, forming a rift valley. Number 3. Continued spreading creates a narrow sea. 4. After continued spreading, an ocean and ridge system are created. My last explanation, there are 5 major subdivisions of the world ocean: the Pacific Ocean, Atlantic Ocean, Indian Ocean, Southern Ocean, and Arctic Ocean. And that's all for my topic for today.